1.3, day number 1, inverse, exponential, and log functions. We're going to talk a little bit about properties of exponentials, rational exponents, as well as inverses. So for any base b and real numbers x and y, the following are true. These are just properties of exponentials, and we'll get to logarithms at some point here as well. But here I would get, we would add those two exponents. Here, when you divide two exponentials of the same base, you'd subtract top minus bottom. Here, this is the same as 1 over b to the y power. And here we would multiply. In a rational exponent, b to the x over y, x is the power, and y is the root. So example, I'd like to rewrite this. There's a power, there's a root. So 64 to the 1/3 power ends up equaling 4. 4 times 4 times 4 is 64. So 81 to the negative 3/4 power. What I'd probably do with this is I would take 81 to the negative 1/3 power to the 1/4. Now that might be a little convoluted, so let me flip it around. I don't know what 81 cubed is, but I do know the 4th root of 81. So sometimes it's in your best interest to think about the different ways you can do this. 4th root of 81, 3 times 3 times 3 times 3 is 81. So the 4th root of 81 is 3. And 3 to the negative 1/3 is 1 over 3 to the 3rd, which is 1 over 27. Okay, so that's how you work with your rational exponentials, or exponents. Is it possible to raise a positive number to a power and obtain a negative number? The answer is no. And a nice clear reason why. Let's take e to the x. No matter how small of a negative number I plug in for x, that graph will never reach 0. Right? If I take a positive number to an exponent, I can never reach 0. Is it possible to obtain 0 by raising b to a power? Well, this it approaches, but never equals 0. So no, that would also be a no. Properties of the exponentials are interesting. The domain for f is all reals, right? So x is a real number. Doesn't matter what it is. Another way you could write that is negative infinity to infinity. All real numbers. Output or range for an exponential, if b is greater than 0, would be the following. Or you could write it in this form. X is greater than, y is greater than 0. Right? Okay, if b is greater than 1, then f is increasing. If b is between 0 and 1, then it would be decreasing. All right, so you've seen half-life problems. You've seen growth problems. If b is greater than 1, it's increasing. If b equals 1, then that's dumb. It's neither. Okay, so the inverse function. Given a function f, its inverse is a function f. This is not the negative 1 power. This is f inverse. Right? That's how you say this, f inverse, such that whenever y equals f of x, then the inverse function of y equals x. Other ways to interpret it, the inverse function undoes the original function. Or if we start with a value of x, apply f to it, then apply the inverse to f of x, the final result is x. Too many words. Basically, if we do the composition going both ways, right, f inverse of f of x or f of f inverse of x, we should get x in either case. All right, steps to finding the inverse. What I always do is I switch x and y, and then solve for y. And this will get you your inverse. Okay? So something cool about inverses is that the domain of f becomes the range of the inverse, and the range of f becomes the domain of the inverse, which you can use to your advantage later on. Find the inverse function of this, f of x equals negative 3x plus 4. Okay, so step one. Right, I'm going to write it in this form. So step number one, I'm going to switch x and y. I'm going to solve for y. And it looks like y equals negative x over 3 plus 4/3. Therefore, my inverse is that, negative x over 3 plus 4/3. Now, how do I prove that that's true? All right, so to prove that that's the actual inverse, here I have f of x, and here I have the inverse. I got to show that f inverse of x equals x, and I have to show that f inverse of f of x equals x from above, right? That's a property we just learned. So let's do that. F inverse of x. So f is negative 3 times x plus 4. Okay, now I'm going to plug f inverse of x into that. So that'd be negative x over 3 plus 4/3. Well, if I distribute a negative 3 to that, I would get an x, I would get a negative 4, and look at that, it comes out to be x. So I've shown on one side that it works. Let's do it on the other side. So into f inverse, which is negative x over 3 plus 4/3, I'm going to plug in f. Let's plug in f. F is negative 3x plus 4. Okay, so I'm going to change the sign. So that'd be a positive 3x and a negative 4/3, or negative 4. So it'd be a positive 3x over 3 minus 4 over 3 plus the 4 over 3 I already had. Those cancel. 3x over 3 is x, and it checks off. So I've confirmed that they are inverses of each other. So I'm going to graph these. Okay, so here is negative 3x plus 4. Okay, that's f of x. Let's sketch our inverse. Okay, 4/3. Oop. That's not going to be all that pretty. Negative 1/3. Down 1 over 3. It'd be about there. And there's our inverse. Okay, what line do these functions have symmetry over? Graph that line of symmetry. Well, they have symmetry over this line y equals x. Right? If I reflected any point, this point, it would match up with that point. Right? So this point I know is 0, 4. So this point better be 4, 0, etc. It maps it across that axis. Y equals x. What is the domain and the range of f? What is the domain and the range of f inverse? Well, their domains are all real numbers. And their ranges are all real numbers. There's not a whole lot cool about this function, because it's a line, but the domain of the inverse is going to be the same as the range of the original. All right, and the range of the inverse will be the same as the domain of the original. So because both are the same, there's not a whole lot of groundbreaking information coming your way on that, but that's how we would work that. All right, when do inverse functions exist? The function f has an inverse when f is 1 to 1, or when every output of f has exactly one input, meaning they're unique outputs. This is checked graphically by using the horizontal line test. Horizontal line test. So if I were to sketch 4 to the x, 4 to the x looks like this. Every exponential in this form goes through the point 0, 1. All right, and it looks like this. If I were to draw a horizontal line, here's what the horizontal line test means. It means it only crosses that function at one point everywhere. Right? As long as you draw a horizontal line, it doesn't cross it more than once, it is 1 to 1. So this one is 1 to 1. Okay? This function over here, this quadratic, is not 1 to 1. It's not going to pass the horizontal line test, right? It's been shifted left 3 and up 1. 1, 2, 3, up 1. General sketch of that will look like this. Okay, so if I drew a horizontal line over here, we'd have issues. It's not 1 to 1. Therefore, its inverse is not going to be a function. Okay, so it's not 1 to 1. You'll see why. Which one is 1 to 1? Which one is not? We just answered it. F is, and G is not. Right? Restrict the domain of the function that is not in order to make it 1 to 1. So let's restrict the domain. And the spot where we're going to want to do that is we're going to want to cut it off right here. So that's where x equals -3. So we could restrict the domain to being either negative infinity to -3 inclusive, or we could restrict it, again, this is on F, or I'm sorry, this is G, I believe, yep, G. We could restrict it to -3 to infinity. Either way, then we would pass the horizontal line test, and our inverse would be a function. So use the equation -x squared minus 3. Let's graph it. All right, so it's a parabola that's flipped over and shifted down 3. Okay, there we go. Okay, won't pass the horizontal line test, so restrict the domain so the function is 1 to 1. Okay, so let's restrict the domain. Let's just color this 2 different colors. So let's go to the domain here is greater than or equal to 0. The domain over here is less than or equal to 0. Okay, so let's find F inverse on both intervals. All right, so first let's just take our 2 steps here. F of x equals -x squared minus 3. So let's write it in this form. And let's switch x and y. Let's do this. Okay, then we'll do this. And then what we're going to get out of this is 2 possible equations for y. So y will either equal the square root of -x minus 3, or y will equal negative square root of -x minus 3. Okay, so now we got to determine here which of these 2 inverses is going to go with, these are the inverses, by the way, right here. Which of those 2 inverses go with which of the 2 restricted domains? Okay, so it's pretty simple to see that the domains on the red portion of the function are negative numbers, right? So our y values are probably going to be negative on the inverse, right? If the domain is negative here, the range will be negative on the y values. So I would say that's a pretty good indication that this would be our inverse on that domain. Right, so our inverse for that domain would be this. Those aren't our y values, that's the inverse for that domain. Okay, the inverse for a positive domain would be the values that come out to be positive range values for the inverse, which in this case would be that. So let's graph them. Let's take the parent function. Looks like it's going to be some kind of reflection shift and then another reflection. I'm guessing the inverse would come out for the red portion would come out to look like that. And the inverse for the blue portion using transformations would come out to look like that. And go figure, that is a perfect reflection over the line y equals x. There's some symmetry here, which is really nice. So in part D, we've now graphed the inverse. And that's it, folks. Have a great day. Looking forward to the next one. Go get them.